Hi, this is my lecture number 30, number 30, and for this lecture, I'll give you an example of how to use Fourier transform and inverse Fourier transform, as well as the convolution theorem to solve the partial differential equation. I'll give you two examples. First is to solve the Laplace equation in the half plane with a certain boundary condition, and the second one I will discuss the diffusion equation. Right, I'll give you first example, the Laplace equation. So this example is in your notes, and alright, so the Laplace equation given as phi xx plus phi yy is equal to 0 for half plane, where phi is a function of xy. Subject to the boundary condition. The boundary condition phi x0 is fx for x minus infinity to infinity, and phi xy goes to 0 as x squared plus y squared goes to infinity. Now, in order to solve this equation, this problem, I might need a couple of well-known results that I think you can establish this. Let me list down those things. First is that if we transform some result on Fourier transform, let's say if you want to transform Fourier transform of u of x, a function of x, it means this is del u del x, of function x and t. This is just is f u of xt s, which is is f I think this is f. This is the Fourier transform of that, which is u st, right? And that's the number one. This one I have given the proof, I think, somewhere in your notes earlier. Let me check that. Okay, here, right, this part here. I think I've given the proof of this, and you can prove the rest of it. And also, we also need f, the Fourier transform of uxx of xt. This is minus s squared f of Fourier transform of x uxt s, which is minus s squared u capital U st big U. And yeah, we need those things. And as well, if I want to find the Fourier transform of u y, I think I better put this y, because this is related to y, so I put it y here. Okay, I put it y. This is y and y for function u. So in our case, we have phi, so you just change that into phi. Let's change that into phi. This is should be capital Phi. Then uy xy, this is del t f of u xt of s del t u sy, and so on. Yeah, for the uyy, differentiate twice with respect to y, xy, this is del 2 del t squared f u y s, this is del squared del t squared u sy, yeah, where u is the Laplace transform of u. Yeah, u is the Laplace transform of u. I can write here f of u xy as this is u s y. And also we need the convolution theorem that we have that earlier. We have the convolution f star g of x, this is 1 over root of 2 pi minus infinity to infinity. You have f zeta g x minus zeta d zeta, and f for the Fourier transform of convolution of g x, this is just fs gs, where f is the Fourier transform of function f and g is the Fourier transform of function g. And the inverse of that, the inverse of Fourier transform f of s g of s, this will give you f of convolution of f and g x. So we're going to use this part. Okay, now let's come back to our problem here. Now the idea is to solve this equation. Yeah, the idea is to solve this equation, the Laplace equation. Now how to do it? First, we use the Fourier transform to transform into the Fourier transform of those equations together with the boundary condition. Now, having obtained the solution for the transform equation, we will invert using the inverse Fourier transform to find what the function phi is. Right? So that's the process that we need to use. Now, okay, from this equation, as I mentioned earlier, that we're going to use Laplace transform to transform that equation. So using the Laplace transform, Fourier transform, Fourier transform of 1. So let's call this equation is 1. This equation number 1. All right. I think and the boundary condition, that one here, I call it number 2. Okay, now for the transform of 1, and we let the Fourier transform of u xy as I say u, sorry, phi, I use phi, right? No, just a minute. phi, Fourier transform of phi xy, let's call this as a phi sy, capital Phi. Then the boundary condition of those, the Fourier transform of this, that will give you d2 phi dy squared minus s squared phi that equal to 0. So let's call this equation number 3. Okay, so if you look at this equation here, so the Fourier transform of this, that will give you minus s squared of phi from here. There's minus s squared of function, and the transform of this part here, that will give you this. Okay, so that's why we have those equations. And the boundary condition, subject to the boundary condition, that we transform the boundary condition here. So we have which is Fourier transform of 2 to the equation of the boundary condition. We have phi s0, that give you fs, where fs is the Fourier transform of fx, and phi sy goes to 0 as y goes to infinity. Okay, so for this you can solve this equation. I don't want to go that detail on how to solve this. You can use either the appropriate method, a variation of parameter, undetermined coefficient, or whatever it is for the second order differential equation. You can use that. Okay, try to work out for this, and the general solution of those, general solution of 3, you're going to have phi sy, this is equal to ae minus sy. Now if we apply the boundary condition here into that, apply the boundary condition, we're going to have, you can see when y is 0, that gives you 1. Then this is fs, so a is equal to fs. So you have phi sy, this is fs e minus absolute of s y. Now the purpose is we want to find the solution of the Laplace equation, which is phi xy. Now to recover or to obtain xy, we need to apply the inverse Fourier transform, right? And then after that we're going to use the convolution theorem. So apply the inverse Fourier transform, So we have phi xy, this is the inverse of phi sy, okay, which is 1 over 2 pi sub 2 pi minus infinity to infinity. So we have fs, we have here e minus y and e I s x ds. Okay, this is a function. So you can see from here, this is the function of the Fourier transform for g, right? The Fourier transform for g. this Fourier transform for f, this is Fourier transform for g. This is the definition for the inverse Fourier transform. So from here, what we can see, the g of s is e minus sy. Yeah, to find g of x, which means we need to inverse those things. We need to inverse g of s, which is inverse of that e s y. Okay, so if you find the inverse of this, that 1 over square root 2 pi minus infinity to infinity inverse of that, so we have e minus s y e I s x ds. Okay, if you solve this, you're going to have 2 over pi y over x squared plus y squared. Without y, I think I've given the example how to find the inverse of one of those when we deal with the Fourier transform. I think inverse Fourier transform, I've given the example for that, so you just need to refer to that example. Yeah, you just need to refer to that example to find the inverse of this I've given in the previous video. So therefore our function phi, because our g is that, our function phi is given as xy, yeah, 1 over, so this is g, this is f, this is g. Okay, and I mentioned earlier that we're going to use the convolution here, fmg. Okay, so f is that, our g is gx or gs is that, with gx is this one. All right, so if x, we want x gx minus zeta, so that's give you just replace for each x with x minus zeta. All right, so therefore you have our function at phi is given as you have 2 over pi here, square root 2 over pi, and 1 over 2 pi here. Then you have 1 over pi, so integrate minus infinity to infinity. So we have f, that one is for f zeta. Then that for g, we have y over x minus zeta squared plus y squared d zeta for y positive. So this is the solution of the Laplace equation, the solution that we're looking for. So this equation, yeah, all right. If you know fx, yeah, if you know fx, the boundary condition, if you know fx specifically, then you can just plug in there, and then you can evaluate those integral. Then you can find specifically what is phi xy, and then you can use the another boundary condition. You can use another boundary condition, which is that, to find the final solution, yeah, the particular solution. So this is the solution of our problem. So that's for the first example. For the second example, where is my second example? Right. There is some typing error in the notes, so I will give you the edited version of these notes later in the Putra Blast. So the next problem is we consider the diffusion equation, yeah, this is the diffusion equation. We have phi t equal to kappa phi xx for x between minus infinity to infinity subject to that boundary condition. Okay. So the second example, we consider the diffusion equation. Which is given as phi t kappa phi xx for x minus infinity x infinity, and the function phi is a function of x and t, and subject to the boundary condition we have phi x0 is equal to, let's say, equal to fx. Then of course we need another condition, x y goes to 0 as xt goes to infinity. Okay, but to solve those, to obtain the general solution of that, we're going to use that condition. Again, the procedure is that we use the Fourier transform to transform those equations. We obtain the solution of the transform of the Laplace transform of that equation, and then obtain that solution. We invert using the inverse Fourier transform as well as the convolution theorem. Okay, so let's do that. We have the boundary condition and kappa is positive. Yeah, kappa is positive. Yes, kappa. So if we define the Fourier transform, let's say phi st as 1 over square root 2 pi. This is full, yeah? In your notes is just half. As I mentioned, this is unedited version of notes. The edited one I will upload in the Putra Blast. That's minus infinity to infinity phi of xt e minus isx dx. And this is the Fourier transform of function phi xt. Then the transform of this equation, so let's call this equation number 1. Yeah. Then using that, then the Fourier transform of 1 will have d phi dt equal to minus kappa s squared phi for t positive, of course, t positive. And from there you can easily solve this equation, because this is the separable equation, first order differential equation, so easy for you to solve. You can have the solution, the general solution of those. General solution is given as phi is equal to some constant a e minus kappa s squared t. Okay, then if you use the boundary condition here, yeah, the Fourier transform of that boundary condition, you have phi s0 that equal to f of s, where fs is the Fourier transform of fx. So if we apply the boundary condition, into that solution, apply the boundary condition, we're going to have phi of st, this is fs e minus kappa s squared t. Now, to find the solution of the diffusion equation, the original equation here, we need to invert that using the inverse Fourier transform. Yeah. Then we apply the inverse Fourier transform. Apply the inverse Fourier transform. We have phi xt, which is the inverse of phi st, and this is by definition is 1 over square root 2 pi integrate minus infinity to infinity. So we have, this is our phi s, so that gives you fs e minus kappa s squared t, the inverse is x ds. Okay, and of course you can see this as the inverse of the Fourier transform of the convolution. All right, the inverse of the Fourier convolution of two function f and g, which is 2 pi minus infinity to infinity. You have f of zeta g x minus zeta ds d zeta. Okay, so f s is the Fourier transform of that. This is the Fourier transform of gx. So we have g of s is equal to, is from here, this is e minus kappa s squared t, and then to find gx you need to inverse those using the inverse Fourier transform. So we have 1 over 2 pi minus infinity to infinity e minus kappa s squared t e I s x ds. Okay, so if you solve this, you can check in the table, in the or you can solve it by yourself. You're going to have that g is 1 over square root 2 kappa t e minus x squared over 4 kt. Yeah, so therefore you substitute this g into those, so you're going to have, so therefore we have the solution phi xt is 1 over square root 4 pi kappa t integrate minus infinity to infinity f zeta e, that one is minus x minus zeta squared over 4 kappa t d zeta. Okay, so this part here come from our g, yeah, because gx is this, so we need gx minus that zeta, so we just substitute x with x minus zeta, so we have those things. So this is the final solution of the diffusion equation problem. All right, so if you look at in your notes, we have another example, which is the KdV equation. I think you can solve those KdV equation. You can work out yourself. So the main point that I want to stress again here is that when you want to solve the differential equation using Laplace transform, so what we do, the first step is that we transform those equations, the given equation using the Fourier transform, together with the boundary condition, and then obtain the solution for the transform equation. With those, we use or we invert to find the solution phi x. We invert those solution using the inverse Laplace transform, and then that will and together with the convolution theorem, that will end up with your solution to the original problem. Okay, so that is a conclusion, and I stop here for this video. Thank you.